So I'm going to do an example for you. This is a graph f of x equals the quantity x minus 3 times the quantity x squared plus 3x plus 9 all over x squared plus 5. So it's important to know that x squared plus 3x plus 9 and x squared plus 5 don't factor with real numbers. You can tell this by setting each of them equal to 0 and try to solve for x. If you set x squared plus 5 equal to 0, you get x squared equals negative 5. X equals plus or minus I times the square root of 5. That's not a real number, so it doesn't factor with real numbers. If you take x squared plus 3x plus 9, set it equal to 0, and apply the quadratic formula, you'll find that you end up with square roots of negatives. So again, it doesn't factor with real numbers. Okay, so this is factored completely if we're just using real numbers. And when we're graphing in the real plane, all we care about is the real numbers. We don't care about complex roots or anything. So the first step was to write it completely factored, and it was given to us completely factored, so I just wrote it down just for your information. The domain of f is all real numbers. Why? Because the denominator is never 0 for x real numbers. As long as x is real numbers, the denominator, the smallest it could be, is 5. Because x squared, the smallest it could be, is 0. And you add 5 to it, right? The smallest that could be is 5. Okay, so the domain doesn't reduce, or I'm sorry, f doesn't reduce because it has 3 factors and none of them are the same. So that's pretty obvious. There's no vertical asymptote for the same reason the domain is all real numbers. Because if you set the denominator equal to 0, you don't get any real roots for that. Okay, the x-intercept is when y is 0. Y is 0 when a fraction is 0 when the numerator is 0. So you just set the numerator equal to 0, like this. And the x squared plus 3x plus 9, if that was equal to 0, as I already mentioned, you get complex numbers, non-real complex numbers. And so that doesn't count. And so you just get x equals 3. Because you just want real number solutions. We're just in the real plane. All the non-real numbers don't count. Okay, so the y-intercept is when x is 0. That's the easier one, usually. And so you just set x equal to 0 in the equation, and you get minus 27 over 5, which is exactly minus 5.4. I just wrote it that way because it's easier to graph because you can see the magnitude of the number. And then I want to look for the non-vertical asymptotes, right, which would be horizontal or oblique, if there are any non-horizontal asymptotes. This one, notice the degree of the numerator. If you multiply this out, the degree of the numerator is 3, and the degree of the denominator is 2. So the degree of the numerator is 1 more than the denominator, so I'm going to get an oblique asymptote. But in order to figure it out, I have to do long division, and that means I need to multiply out the numerator. Okay, so multiply out this numerator. And when you do that, you find out that it's just x cubed minus 27. It's a difference of 2 cubes. If you remember how to factor a difference of 2 cubes, it's exactly like this numerator. If you factor x cubed minus 27. So I just multiplied this out, wrote it down, but then I was missing an x squared term and an x term, so I put 0x squared and 0x in there. And then for the denominator, I'm missing an x term, so I put in a 0x. Now I take x cubed over x squared, and I get x, and I write it above the x term. And then I take the x, and I multiply it by all 3 of these, and write them below. You get that? And then you subtract the whole quantity, right? And then be careful subtracting. The first 2 terms are just 0, so any leading terms that are 0, you just leave off. And so I end up with negative 5x. And negative 5x is a smaller degree than x squared is. So I'm done. I just need to bring down the minus 27 for the rest of my remainder. So my remainder is minus 5x, or negative 5x minus 27. And so we put that over the divisor, and I factored out the negative and put it in front. So I get x minus 5x plus 27 over x squared plus 5. Now that fractional part I don't really care about, because as x becomes a large magnitude number, that fractional part becomes 0, because the degree is 2 in the denominator and 1 in the numerator, right? So I just get y equals x, and so that's the asymptote. It's a oblique asymptote, y equals x. Okay? So one reason I'm doing this example, so you could see that oblique asymptote business. So now I'm going to try to graph this thing. First I graphed the y-intercept. You can do this in whatever order you like. I usually try to get the asymptotes in pretty quickly. There's no vertical asymptote here, but there is this oblique asymptote. So I think I did the oblique asymptote next. I could have done the x-intercept. I don't know why I didn't, but I just wanted to get that y equals x in there. That's an asymptote. And then I sketched in the graph. It looks like that. And I kind of missed a little bit here. That's supposed to go through 3, because the x-intercept is 3, right? Well, the intercept is actually 3, 0, but it should go through that point there. How did I know it was shaped like this? I graphed it on my graphing calculator. Now, this here looks like it's the bottom of this hump, and it turns out if you apply some calculus to this stuff, which we're not doing, but I did anyway, just for fun, it turns out that actually is the bottom of this little hump. It's what we call a local minimum. There's a local maximum here, which is just the top of this hump, but when I went to calculate it, it comes out a really crazy number, at least as far as computing the exact number, which is all I was really interested in. It's a really crazy number, but it's around in the right place. It's about in the right place, somewhere around -4, or I'm sorry, -3, -4, somewhere around there. Anyway, we worry about that in calculus. You'd have these extra things you have to look for. You'd also have where this changes from curving up to curving down, which would be somewhere in here, and same thing over here, somewhere in here. And you would also compute those. But in algebra class, this is actually a fairly short list. It looks kind of long, but comparatively, it's actually a fairly short list of things to find to graph. It's really learning the properties of the function is really what's most important here, more so than actually graphing it. Because graphing it, you can just use a graphing calculator, right? In fact, that's how I check this. I just get out my graphing calculator and graph it.